Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, welcome everyone. It's a great pleasure to again introduce Emery Berger from the University of Massachusetts. Emery is here for a month and he's still here for another week, so if you want to talk to him, you're welcome to. Emery's done a lot of interesting work in systems. We heard last time about Automan, and this time we're going to hear about Stabilizer, which is a very creative way to slow your program down but make it better. So, thanks, Emery.
Thanks. Yeah, it turns out. Thanks, Ben. Yeah, that was great. It's a lot easier to slow down programs than to speed them up. So I have a rich career ahead of me. All right. So this is some work on performance evaluation that just recently appeared at ASPLOS. I actually could not attend ASPLOS this year because I was sadly in Rome. So it was Rome, Houston. But this is joint work with yeah, right, exactly. So my student Charlie is the lead grad student on this work, the only grad student on this work, and he presented for me. So and he, I hear, did a great job. So hopefully I'll do as well. You know, I think most of us in this room actually care about performance, right? A lot of people in general, I think, when you write your program, you think, or your optimization or your system, you say, well, we really would like to show that in fact speeds things up, not slowing things down, right? So the problem is, it turns out that largely, this isn't really necessarily everybody, although I include myself here, many of us have been doing it wrong. All right, so we've been doing performance evaluation for years and years and years, and we actually have been making some crucial errors. In particular, things that we think are best practice, like running things repeatedly and getting error bars and showing all these very pretty graphs. That's not actually enough. And the reason is that there are things that really are lying under the covers that we're not actually seeing that have a huge impact. And they have such a huge impact that it actually makes the results that we're reporting potentially meaningless. So what do I mean? So in particular, there's this problem on modern systems, which is that the layout of the objects in memory, the objects include your data and your code, dramatically affect performance, right? And even very, very slight things that you might do to your program actually have a pretty serious impact on layout, right? So if you change some of your code, it moves things around. If you change some allocations and so on, it moves things around. And right now, when you run your program a bunch of times, there's really no way to isolate this effect. And this effect is super, super important. So the goal of Stabilizer is to eliminate this effect. All right? And by eliminating this effect, it's going to enable us to do what we call sound performance evaluation. And I'm going to explain what that means. All right? And not only am I going to explain what it means, I'm going to show you some case studies that demonstrate the value of using Stabilizer and taking this sort of sound performance evaluation approach. Okay? This.
I have to argue already.
All right, just one second. Let me finish up the slide. So the case study. Yeah, really. The case study I'm going to present is an evaluation of LLVM's optimizations. And so I'll show you what the impact is of using Stabilizer and how it lets you understand things differently. Catherine, go.
What happens if your performance optimization is to change the layout in order to prove performance?
Yeah, so
that's.
So
then randomizing layout defeats the purpose of what you're trying to do.
Yeah, so I'm actually going to talk about that a little bit later. But it is true that if your goal is to do something that affects every single aspect of memory layout, not just the data placement, but also the code, and also globals, and also the stack frames, then Stabilizer would be undoing those things. However, if it only attacks one, which would be normal, like typically data, for example, or possibly code, then Stabilizer allows you to isolate all the other effects.
OK, so you have a base, so I'll derail you just a little more.
Sure.
You have a base system that does code layout, which is trying to give you good cache locality.
Right.
But then you do a data layout optimization. And so do you want to screw up the finely tuned code layout as well to see if your data layout is independent of that? Like that's the key thing?
So So here's the thing. So first, I think it is, there's the sphere of optimizations like the ones you're describing, right?
Afraid of them.
No, no.
I want to make them.
No, I understand. Now, I'm not saying that they're scary, although, Then there's many, many other things that people do with their code, right? So they go and they manually try to optimize their code. Or they're writing their code and they add features, and the features make the program go slower, right? So this is a performance regression. Right? So the problem is that you run your program, and we'll get to this in a second, but you run your program and you see some performance change and you draw a conclusion. And that conclusion may be completely unfounded because of all of these other confounding factors. Right? So these confounding factors are all of these artifacts of running on real systems today. When it comes to very, very precise things that actually depend on memory layout, the question is, does it depend on every single aspect of the memory layout or not? Things like stack frames typically are not subject to these kind of optimizations. It depends. Code placement, definitely. Heap object placement is iffy, right? So there are a number of these factors that you can sort of say, all right, I really care about these factors. Don't change those, but change everything else. All right? OK. So I'm going to go ahead and focus first on this issue of memory layout and how this affects performance. OK? So of course, some of you are aware of this, but that's fine. So suppose I've got a program. So here's some chunks of code. And let's call this program A. And then what I'm going to do is I'm going to actually make some modifications. Right? So I move some stuff around. I refactor some things. I modify some functions. And now I call this new program program A prime. All right? So the question is, so say I meant to do this to make it faster. Right? Like I was like, oh, wait, there's something here I can really speed up. I can make this go way, way faster. OK. So what do I do? So I run it. Right? The green one is the new one. The blue one is the old one. And it's a little hard to see the numbers here. This one says it took 90 seconds. And this took 87.5 seconds. All right? So which one's faster?
A prime.
OK, so A prime is faster. What's that? No idea. You have no idea. Man, see? All right. So this is the problem, right? Everybody's like, it's a trick question. It looks faster, but I'm scared. All right. So this is really how we formulate this, right? We say, is A prime faster than A? And you look at the time, and you look at the bars. You say, oh, this bar is to the left of the other bar. Fantastic. OK? So clearly, A prime is faster. And in fact, in this case, the difference is 2.8% faster. All right? So you say, OK, 2.8% faster. All right. What's the first obvious objection to this?
One run.
One run. OK? I ran it one time. So the question is, well, what about variance? What if there's some sort of noise in the system? Is 2.8% really something that overcomes that noise? So now I run it 30 times. OK? 30 is kind of a magical number. It turns out for many of these studies. So we go ahead and we run it 30 times. And now we look at the variance. And the variance is pretty tight. Everything looks good. Looks like A prime is faster. In fact, the means, not just the means, but the extremes, the max of one and the min of the other, still 2.8% difference. All right?
Why is it 2 bars for the green and 3 for the
so here, yeah, so this is just, there's actually 3 bars here and 2 bars here, but this is just the distribution, the empirical distribution of running this code.
Oh, it just happens to be.
Yeah, that's right. Just happened to be that way. It's really just an artifact of binning. OK, so why is A prime faster than A? Of course, it's because I'm a genius programmer, and I made it 2.8% faster after 3 weeks of effort, right? Terrific. So it could be the code change. And that's what we generally assume, right? Like, I made this change, and good things happen. But it could just as easily have been the new layout. Right? I made a bunch of changes here, moving around functions, changing the size of functions, that had a significant impact on where these things end up in memory. And one of your colleagues, Todd Mitkowicz, back in 2009, presented a paper talking about how layout biases measurement. All right? So what kind of things can you do, and this is what Todd showed, that can have dramatic impacts on the performance of your program without changing code? So you can go into your makefile and change the link order. So just changing the .os, like foo.o, bar.o, or bar.o, foo.o, can have a substantial impact on layout, right? It moves all of the functions from one place to another. environment variable size. This one is completely bizarre. So it turns out that when you run a C program, it actually goes and copies in your entire environment and then starts the program after that. All right? And that means that changing your environment, and changing your environment can mean changing your current working directory, the time of day, the date, all of those things actually move all of your code in memory. So you might think, all right, come on, we're moving the stack.
Your Java runtime has a little C component. The managed runtime has the same problem. It's not just the C program.
That's true. Actually, so Catherine has a good point. It goes even further because not only is Java or .NET actually a C program, it turns out that the runtimes actually do import the environment. And they import it into your heap. Right? And a lot of the code gets compiled onto the heap, which means that your code placement and your data placement are still affected by these environmental factors. All right, so you might think, all right, come on, how much of a big deal is this going to be? Well, it turns out, as Todd and Amr showed, and Peter Sweeney was on this paper as well, that the impact of these changes can be greater than the impact of -03. And these are very, very coarse-grained changes, right? This is moving all of the data just on block, or taking a whole bunch of functions and moving them separately. The changes that you make as an individual, your sort of very, very fine-grained changes, can have a much more deep impact. So what's going on? So the problem here is the cache, right? So you have these caches. Caches are awesome. They make your programs run faster, right? You have these very, very fast memory, but it's relatively small. And in some cases, you can end up with some sort of catastrophic collisions in the cache, right? So you go and you have your code here. These two pieces of code are hot. So they end up, unfortunately, mapping to the same cache set, and you get conflicts. So they don't all fit in cache at the same time. It runs slower. When you change your program, by luck, you could end up actually getting an empty space in that set, right? So the code is not there anymore. The hot code has moved elsewhere. And now we have no conflict. All right, so this can happen because of caches. Caches aren't the only source of this sort of problem. Branch predictors suffer from the same sort of phenomenon. Branch predictors depend on program counters to sort of key into hash tables. Then there's TLB, right? Translation look-aside buffer. Same thing. It's address-based. The branch target predictor. I could fill up the slide, basically, with all of these things that use essentially addresses as hash functions. So really, anything in your hardware that has a hash function suffers from this problem. Yes?
The TLB is not fully associative.
So the TLB is fully associative, but it depends on where things lie, right? So if you think about it, if I have a function that spans 2 pages, right, then I would need 2 entries. But if it's all in one, then I would only need 1 entry. Right? So you're right about the address not being the issue, but it's about sort of fixed size resources as well. All right? And the placement of things in memory. All right, so now that you've seen all this, if you hadn't seen it before, let's go back and think about this. We're asking this question, is A prime faster than A? But now we know that there are all these weird confounding factors. So what do we actually do in practice? In practice, we essentially go and we find the one layout, right? We don't try all the environments. We don't try all the link orders. We just ask one person, right? So it's sort of like we ask this guy, all right? And it's like, hey, it seems to be faster, right? It's 2.8% faster. We're done, right? But here's something you would never really do in practice, right? You wouldn't go ask one person for their opinion about something. Say, hey, what do you think? Is this faster? Yes, 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 right? Do it 30 times. Oh, I have so much more confidence that it's faster, right? So what you'd really do, you really want, is you want to sample. You want to sample the space of all of these things, right? All these different layouts, all these different guys. Some are going to say it's slower, potentially. Some could say it's the same. But you really need to cover the space to find out what reality is. So there's an objection that people often come up with at this point, which is, hey, I like the faster guy. Okay? The faster guy is my friend. I just want it to be faster. Now, and this is not just like I want it to be faster because I want to publish a paper, right? Although there's that. It's also, look, you ran it faster. It's like, well, I don't care about these other layouts. Maybe I just want the good layout. I want the faster layout. So what if we just sort of stick to that layout? We say, this is a damn good layout. We like this layout. Let's keep it. All right? So we're only going to talk to Bob, which means here we're only going to use this layout. OK, so that sounds good. There are problems with this approach. Suppose you upgrade your C library. You kind of have no control over this, by the way. It's like time to update. There's some bug fix. This happens all the time. Microsoft C runtime gets upgraded, whatever. Libraries that you depend on get updated. That changes your layout. All right? If you change your username, not you changing your username, but somebody else uses it, right? That changes the size of your environment. Right? So I actually had this experience myself with a student where I proposed an optimization, and the student came back and said, it doesn't work. It makes things slower. And I said, that can't be true. And I ran the program, and it ran faster. He ran the program, it ran slower. We ended up running it on the same machine, 2 different windows. And his was slower, and mine was faster. And his username was longer than mine. That was the only difference. So if you change the environment variables, then everything worked out great. So this is kind of brittle, let's say. Or everybody could just canonicalize and have the same length username. So we could do that. That's one possibility. All right? So yeah.
Or we should find optimum usernames.
We should all, exactly, do a search. That's right, for every program on Earth. That's right. I agree. Yeah. Well, as you've already heard, it turns out my username is optimal. So, yeah.
You have to make sure that your program layout does not depend on your environment variable. I think that's
So-
probably an easier fix.
Right. So in fact, that's not so hard to do. Right? So you can actually make it so that it doesn't depend on that. But all of these other little factors, like you change one line of code in your program. You change a library. Right? Your libraries are getting shifted out from under you all the time. There's all these different versions of all these different DLLs. And a slight change in one changes everybody's layout. All right? The new directory is another phenomenon. Again, same thing with the environment variables, et cetera. All right? So layout is really brittle. And it's brittle not just, I'm running my one program. You've got the whole execution environment. You're going to make modifications to your program. It's going to go through different versions. It's always changing. So you can't really stand on firm ground and say, I got a 2.8% performance improvement, right, if all this stuff is happening. All right? So layout biases measurement, great. What do we do about it? So it's bad news. Can we eliminate it? And the answer is yes. All right? And I'm going to show you how we do it. So Stabilizer is the system that we built that directly addresses this problem, right? Memory layout affects performance. This makes it hard to evaluate. Stabilizer eliminates the effect of layout. And I'm going to show you that by doing this, you actually can do what is really sound performance evaluation. All right? So what does Stabilizer do? So as Catherine already spoiled the big reveal here, right? So Stabilizer randomizes layout. So what does it randomize? It randomizes pretty much everything it can. So it randomizes the placement of functions. It randomizes stack frames. It randomizes heap allocations. And it actually doesn't do it just once. It repeatedly randomizes this layout during execution. And this turns out to be crucial for reasons that will become obvious later. But basically, when you do this, you eliminate the effect of layout, because you're sampling all of these different spaces of layout randomly, right? If it's completely random, it can't bias the results. OK? So I'm going to walk you through a few of the mechanisms at a very high level. You already know that it's possible to randomize the heap. This is something that I've been doing for a little while now. I'd be happy to explain offline. Here's some of the other stuff we do. So with stack frames, we actually modify the compiler so that instead of doing this usual thing where you call function main, then foo, the stack frames are always adjacent. What happens with Stabilizer is it actually adds these random pads. And these random pads mean that the stack frames start at different positions. OK? Let's see. When it comes to function placement, you have your basic function placement that the compiler gives you, where it jams everything contiguously into memory. What we do in Stabilizer is we install trap instructions at the very top of these functions. And then we randomly find places to put the functions. We make copies somewhere else randomly in memory. And we change the trap into a jump. So if you go to execute that particular piece of code, you'll actually end up executing somewhere else. We keep this little relocation table off to the side, because all the functions that foo may reference could also move. So this will give us their addresses. So when we go and we invoke Baz gets moved somewhere else, and so on and so forth. So when you're running your program, Stabilizer will actually go ahead and do re-randomization. So re-randomizing for the stack is pretty straightforward. You just do different random paths. For functions, it's a little more subtle. So the timer goes off, and it goes and it reinstalls the traps in the original locations. These are the old randomized locations. These have to stay around. They're sort of potentially garbage, but somebody could be running in them right now. They could be on somebody's stack. So it goes and it generates these new versions. And periodically, after actually during this re-randomization period, Stabilizer walks the stack looking to see if these things can be reclaimed. Yes?
So you have a little relocation table at each function. But why do you need it? Because everyone would otherwise just call in the original location and jump, right?
That's a good question. So I'm sorry I didn't make that clear. So when you're in this thing right here, initially it goes to the original location, and then it overwrites it and jumps to the main location all the time. So it avoids an indirection.
Just the performance.
It's just for performance. That's right. Yeah. Yeah.
Why do you need to change placement dynamically? Why can't you do it statically once per compilation? So that every time you recompile, so you have different versions of the program, and then...
Yeah. OK, so there's one very sort of easy answer for that, and then there's the sort of deep mathematically motivated answer. The doing it statically, compile time, sort of this is the weak answer. Experimentally, this is a pain in the ass. Right? So if I want to go ahead and test my optimization, I have to recompile all of my code, and every single one will correspond to one sample. So if I do it this way, then I actually get to sample a large space. But it turns out that there's a statistical benefit that you get, which is really huge from doing this re-randomization, which I'm going to get to in just a couple slides. OK? So just hold that thought for a few slides. Dan.
That's okay. So one more, hopefully quick question.
Yes.
Maybe you get to it. So by, again, the relocation table, you kind of change how foo prime calls bar.
Yep.
Because it won't be like this direct call, it will be now more indirect.
Yep.
It really changes, could potentially affect branch prediction and all kinds of things in the hardware level, right? So you kind of change.
Right. So so when you do a jump, the branch predictor is already, obviously if it's a static jump, then there's no branch prediction necessary. However, if you do a jump through an address, then there is actually a branch target predictor. These work very well. So I mean that part in terms of performance is not really as much of a hit as you might think, and I'll get to some performance numbers very soon.
Okay. But I mean, you do change something.
Yes, we're changing something. You're right.
You'll miss initially, but then if you're always jumping to the same place for a while, then you'll hit, right?
Right. I think that your objection is somehow that we're changing the program.
Hey, you're changing the program.
Right. Yeah.
No, the randomization has overheads that will swamp the other ones. I think that's a better. That's the real problem that could happen.
Well, right. So the concern, right? That's right.
Just making everything slower has been
right. So the concern, that's right. So the concern that you're getting to is another concern that I'm going to address, which is whether doing these changes actually affects your analysis. OK? So obviously, I'm going to argue that it doesn't, but we'll get there. All right. So now that we have this in place, this whole thing of, and bear with me, let's everybody assume that this is all going to work out great and it's going to be reasonably fast and everything is going to be fantastic. I'm going to talk about performance evaluation. Yes, Mike.
How do you know that you've addressed all the things that create these problems that you're trying to...
Right. So the question really is, all right, so there's all of these different confounding factors. How do I know I've addressed all of them? So I haven't addressed all of them. So I can give you an example of one that we haven't addressed, which is that you could randomize the senses of branches, for example. Right? We don't actually go into functions and change anything about the code. Inside a function, right, you could imagine that there's some impact of having things in relative locations. Inside heap objects, right, inside stack frames, there's relative positions that we aren't disrupting. So there are things we already know we aren't doing. It turns out that these, I don't think that we're covering the whole space. We understand the space we're covering, and we can address it up front, which is a huge advance over saying, well, overdoing nothing, or saying here are a couple selected factors that we account for. Okay? And one of the things that we observe, well, you'll see what it does to execution times, and it gives us some characteristic of execution times, which gives us very, very strong reason to believe we are covering things very well. Okay? All right. OK, so let's go back to performance evaluation. So we run our things 30 times. But now when we run them, because of randomization, we have a bit broader of a distribution. OK? So now, is A prime faster than A? What do you think? How many people say, yeah, it's faster? I see a couple nods and smiles.
5% confidence, it looks like.
Well, this is, you're saying you're measuring this, this chunk of the curve here. It seems faster. All right. How about now? Is it faster now? People seem a little more skeptical. Looks like it. How about now? All right. Now we're all like, I'm not so sure anymore. So the problem is that this is not actually the way that one should proceed to say these two curves are different. Right? It seems like we all have kind of an eyeball metric. Right? We say, if the curves are really far apart, then it's good. And if they're close, I'm a little less comfortable about it. But in fact, this is not really the way that people do things from a statistical standpoint. So, so what people do this is what people in the social sciences do and people in biology and all of these folks do, they're faced with these kinds of problems all the time. Right? So I have a drug. Does this drug have a significant impact on this disease or not? Right? What they don't do is eyeball it. Okay? They don't say, seems good, right? Everybody use this drug, right? So what they do is they adopt this hypothesis testing approach. All right? So the way a hypothesis test works is actually quite different. So we don't ask the question, are these two different, right? Or is this faster than the other? We say, if we assume that they're the same, okay? This is called the null hypothesis. Assuming they are in fact identical, what is the likelihood that you would actually observe this kind of a speed up due to random chance? All right? That's the statistical approach. So it turns out that this sort of thing, often we make these assumptions of normality in biology and in social sciences, and it's very easy to compute what the likelihood is that you're going to end up with this null hypothesis appearing to be true by random chance. And you all have, I imagine, seen this curve. This is the classic normal distribution. And you say, the odds of being more than 3 standard deviations away from the mean due to random chance are less than 0.1%. All right? So by giving us this situation, so we do this, this randomization, we do all the stabilizer stuff. Now it's actually going to put us into a position where you can ask the question exactly this way. So what we're going to ask is, what is the probability that we would observe this much difference just randomly? All right? And the argument that everybody makes statistically is, if this probability is low enough for some definition of enough, right, then we argue that the speed up is real. And because we've randomized the layout, we know that this speed up is in fact not due to memory layout. Okay? So there was this question before about why not just use a static one-time randomization, right? So what does re-randomization do for you? So this is an empirical result of execution times with exactly one random layout per run. And you can see that it spans some space, but it's fairly uneven, right? So this is just, we start off, we do a randomization. It's a one-time randomization. We run with it the whole time. OK? Here's what you get when you do it many random layouts per run. And you can see that curve looks very, very different. Right? It actually has, it's a nice peak. It has a tail. It's unimodal. What's going on? So stabilizer, the way stabilizer works, it generates a new random layout every half second. All right? And if you think about it, what's happening? You've got your whole program, and it's composed of a bunch of these half-second epochs. Your total execution time is the sum of these periods. So it's the sum of a sufficient number of independent, identically distributed random variables, right? Those are approximately normally distributed. This is the central limit theorem, right? So doing this randomization repeatedly actually means that you can use the central limit theorem.
So
yes.
if I take this program, compile it, and ship it to a customer, right? It's
Yes.
going to run on some random configuration, but that remains the same for the entire run of the program, right? Because what you have generated is this Frankenstein runtime that is not available to anybody else other than you.
Wait.
Right.
So I can't ship with this, is what you're saying?
I'm assuming that you're not going to ship with it.
Oh, but you could.
Well, I think that's an independent question.
Okay.
Right?
Is it identically distributed?
But you could design like hardware that is randomly
You could.
layered. You could, but,
Yeah.
but let's see.
It's another very
let's
good
have.
assume that that's
Yeah.
not happening. right?
Okay.
Then I would claim that I'm actually running, that is creating lots of static configurations and then running each one of them like 30 times and then doing the sum of over all that. If you do the sum over a large enough random configuration, you should also get the same normal distribution.
What is large enough for you?
I mean, you do it till you get this normal distribution, right?
Okay.
But center limit theorem starts working for you.
So what is your...
So I think the reason why you're seeing this is just that you're able to explore a lot more lot more configurations if you're changing it dynamically versus what you're doing at static.
That's right. So I think I think you're making an argument for using stabilizer, right? So what you're saying is, boy, you could get a lot more experiments done a lot faster by using stabilizer than by getting a one-time randomization with a whole program recompilation and doing that over and over and over again.
No, the evaluation, whether I spend like 20 seconds or 20 days, it's not a question, right?
I think it's a question for a lot of
people. Get the
people,
right
but okay.
measurement, right?
Yeah. So, but then what do you do with that result? I think, are you saying that we're not going to use this to do the hypothesis test, or you are?
No, I'm just saying that, actually having a static configuration is much closer to what the customer is going to be running. So that's probably a truer measure.
But, so which one are we going to ship?
Well, you could randomize it on the customer. But his point is only that you can eliminate some of this overhead because you're doing the re-randomization.
Sure.
And that's closer to what the real.
Oh, well, so there's a
it-
question, there's overhead and then there's randomization. So I thought what you were actually going to argue when you first started talking was that you were going to say, I don't want a curve, right? I don't want a curve. I want some point in the space, right? And I want that space to be, probably one of these sort of extreme to the left points in the space.
Right. So my only argument is go to the previous slide. The one with had two bins and a nice normal curve.
Yeah.
With the dynamic.
Yeah,
Yeah.
this
I
one.
think you're
Yeah.
seeing this just because you're not running enough random layouts.
Yeah, so let me be clear. It's not just the code that's being randomized here, right? It's the code, it's the stack frames themselves, and the heap objects. Like the heap allocations are actually quite randomized. It's not as randomized as diehard. So diehard has this very, very strong randomization property. We actually install what we call a shuffling layer on top of a conventional allocator, and it generates a lot of entropy. So there's actually a lot of randomization happening here. So in the data space and in the code space.
But would you get maybe a different distribution if you did Madan's thing than you did your stuff?
So if you just randomize the code, you won't get as much of a sample of all of the layouts, right? Because you would be still sticking with the same memory allocation. You'd still be sticking with the same stack frames. Right, so this does more extensive randomization than just code.
Something you really get, or this is just to
This is an empirical result.
And how many runs are in the blue thing?
This is 30 for each. Okay?
But maybe Madan's point is just that unless you ship stabilizer, unless you ship your code with stabilizer, it may be that so many of those points are coming from the places where you're going to have layouts that would never correspond to any real layout, because the real layouts don't have these paddings. The real layouts don't, pack in this. It's some.
Well, they could.
random arrangement
Well, of course, it's possible, right? Because the randomization can lead to anything that's available through randomization is also a possible real state, right? It's just maybe a low probability state, but it's randomly exploring all of the state space, right? But I think that
your random states always have some padding between, say, the stack.
Well, but the padding can be 0.
But, for example, you put in new libraries, the linker changes,
Yeah.
the layout. So at the deployment site, like you could try to explore and move yourself into the right portion of the distribution space into something that's unlikely in both, unlikely to get randomly, but good performance, right? So you could try to do some optimizations that push you over there.
Right, that's
but
right.
if you're just shipping something, you have to say, oh, I could be any place in this curve rather than the place I had with my one testing, because that's just one sample.
Right, and remember, so what the,
So I think that's the most interesting thing. Like,
Right.
We'd like to say we're always over there on the.
Yeah, we'd always like to be here or something.
That's right, in terms of performance, and that's the distribution over time.
Right.
But you can't guarantee.
Yeah, and it turns out, as we'll show, that in fact there are many cases where throwing stabilizer into the mix because of the randomization actually turned out to improve performance. So it improved performance because the actual compiler and whatever the memory allocator and whatever the libraries and whatever the state of the world was, that was actually less than the mean, right? Less than the mean. It was higher than the mean execution time. And stabilizer tends to regress towards the mean. Yes?
Do you happen to save the layout as you randomize them? And look at the performance of each of them at the end of the run?
Yeah, so this is something that my student Charlie is actually working on right now. So Charlie is in fact doing more or less what Catherine described and what you were sort of suggesting, which is what if we could deploy something that did this randomization and actually deliberately targeted the left extreme, right? And so it can observe these things. Essentially, it's doing online experimentation and then steering the execution that way, right? But this is unpublished work that's not out yet. So. OK.
Is it submitted?
It is not in submission right now. Yes. So everybody jump on board, just like download Stabilizer and beat us to the punch. Actually, I will say that using Stabilizer to do this, because it does add some overhead, turns out to be not the best approach. So Charlie naturally wrote his own dynamic binary instrumentation system. Yes. So good luck with that. That's not easy.
We can write instrumentation.
Okay. Yeah, but it has to be anyway. So yes, I know. All right. So, okay. So let me go ahead and show you what happens when we use Stabilizer. All right. So we went and we decided to try Stabilizer with spec. All right, and LVM. And in particular, what we wanted to understand was what are the effect of these different optimization levels. So I think that most people have a sense that optimization, certainly the layman thinks 01, pretty good, pretty fast, right? Doesn't take long to compile. 02 takes longer to compile, but produces better code. 03 takes a long time to compile, produces somewhat better code, right? There's a sense it's not a linear increase in speed, and certainly not a linear increase in compile time, but that it does something good. So we wanted to see if that was in fact true. So we ran this across the spec benchmark suite. We did it on each benchmark, and then we also did it across the entire suite. Okay? So the first thing we did is we built the benchmarks with Stabilizer. Stabilizer is a plugin for LVM. You can invoke it just like an ordinary C compiler. It's SZC. If you run it like this, then it randomizes everything. However, you can optionally choose one thing that you want to randomize at a time. So this addresses Catherine's concern. What if you care about a particular thing and not all of the possible randomizations? The default is all of them are on. So that corresponds to code and heap and stack frame randomization. Okay. So it turns out that there are good reasons not to randomize globals, and it's a pain in the neck. But
Addresses are in the code.
that's right. That's right. So it's actually a lot harder problem to randomize. Okay. So now we run the benchmarks. Okay. So we run them as usual. We run them 30 times each. But this time we drop the results into R. So R is this statistics language. All the graphs you see in this presentation were actually generated by R. It produces lovely graphs. And it is the tool that statisticians and many social scientists and biologists and so on use to do analysis, statistical analysis. All right. So we get this result. All right. Is A prime faster than A? Obviously, this is the wrong way to do things. So we do the null hypothesis construction. We say if A prime equals A, right, then we're going to measure the probability of detecting a difference at least this large. So what's the way that we do this in R? We use something called the student's t-test. So the student's t-test, this is how you invoke it in R, pretty simple. And it allows you to say, well, if the probability is low enough, and the standard threshold in everywhere is this arbitrary point of 5%. You can choose whatever you like. So if this probability is below 5%, then we reject the null hypothesis. And the null hypothesis is that they're the same. All right, so that's the name of the game. The name of the game is we're going to try to reject with very, very high probability, high confidence, I should say, that the null hypothesis is true. OK? And what that means is that in this case, that whatever we're observing is not due to random chance. All right? OK? In other words, the difference is real. So here are some runtimes for -02 versus -01. These are speedups on the y-axis. The x-axis is ordered increase in speed of all of the spec benchmarks. And you can see that so all of these things are green. These are the error bars. These are, I think, actually don't recall the percentage around the error bars. I think it's 1 standard deviation. All right. So all of these are statistically significant. And so you can see that in some cases you get a statistically significant huge increase in performance. That's for A star. In some cases, here actually I can't see if it's red or not. I think that might be the one that's not statistically significant. Not too surprising, right? It's a very, very small difference. But here we actually get statistically significant performance degradation from using -02. All right? And it just turns out that the layouts that these guys ended up with were, it's like, well, there's this huge space. They end up in some layout. That layout turns out to be, maybe it was lucky back when the person did the implementation of -02. But it turns out not so good right now. OK?
Because you have some set of benchmarks, and sometimes you slow some down, right? And on average, you have all these benchmarks.
All right. So yeah, all right.
But you could still choose to turn this optimization on, even though it doesn't speed up everything.
I see your point. Right. So your argument is, the argument is that, well, all right, across a suite, it's not going to have this much impact, right? Maybe it doesn't improve everything.
Right.
And some things it degrades, right? So I think that for -02 versus -01, this is pretty surprising, because -02 is pretty bread and butter optimizations. I think that if you presented the optimizations for -02 to almost anybody versus -01, you would think these are going to improve performance. And they don't. Yes?
So this graph is with stabilizer or with?
This is all with stabilizer.
Oh, with.
OK?
How would the graph look without stabilizer?
So
one configuration.
yeah, so we actually ran this this experiment. I'm trying to remember. So I think that these speedups are actually speedups. I'm going to have to try to remember. I would have to look at the paper. I can't remember if the speedups are with respect to the stabilizer build or with respect to the actual original execution. We definitely observe cases where these optimizations slow things down, and when you throw stabilizer at them, it makes them run faster. So it's a bit of a weird issue. But yeah, I would have to check.
Pretty disappointed in 02 too. I thought it was much more, like the improvement.
Yeah, it's not. Yeah, it's not a huge amount. I agree. But all right, well, let's go to 03, right? We're going to crank it up.
This is on one machine.
Yes.
Configuration.
Yes, that's right.
Who knows
Absolutely.
when they wrote these and what the machines look like.
Yeah. No, so that's an excellent point. And that's something that's totally out of reach for stabilizer.
Right.
So you could do this with a simulator in conjunction with stabilizer, something like that. But you can't, like stabilizer is still observing the execution on your actual machine. And it's having this effect of disrupting, the memory layout. But, if you have a machine that has a 1 megabyte cache, and then you go to a machine that has a 16 megabyte, right, L3, the performance is going to change dramatically, right? So, and there's no way to account for that. Yeah.
O1 is sort of the debug.
-0 is actually the debug. -0 does nothing.
Okay, doesn't.
Okay. -01 does some very, very simple things. -02 does more advanced things. Especially register allocation, as well as inlining.
Did you measure his -0?
Yeah, -0, it turns out, well, it's so slow that measuring it for the entire suite would take months. So we didn't do it. Yeah, it's bad. OK, so here's -03 versus -02. So this is the same axis as before. So I'm going to make the axis 10 times larger so we can actually see what the differences are.
Great for research papers.
Yeah, yeah. So anyway, you can see that these performance differences are quite small. Now, one of the things that's interesting is this is a very, very small difference, right? But because we're using stabilizer, we can actually say this is statistically significant, and this one is not. And the eyeball test, you'd be like, you know, especially this eyeball test, like totally insignificant, right? Because it's so small. But that's not really how these things work, right? So we actually get these statistically significant improvements, and again, some statistically significant degradations on the left. And it's kind of a wash in the middle. It's interesting that there's this one, which appears quite large, but is actually not statistically significant. OK? All right. So what do these results mean? So right now, I've presented results on a per benchmark basis. OK? But that doesn't actually tell you what the difference is between -02 and -03, because this is a point-wise comparison. All right? So what we actually do is we need to go ahead and run all these things 30 different times, right? LBM, A star, et cetera, et cetera. We get a sequence of graphs, right? So this is when we aggregate them. Before, what the results I just showed you, we were actually looking at here's one benchmark, compare it to the benchmark with and without this treatment. I want to know something about O3 and O2 in general. And what I showed you just now is actually not the way to do it, right? This is sort of what we want to know, right? Is O3 faster than O2? And you know, looks like it's slower here, faster here. And you're like, oh, sometimes it's good, sometimes it's not. But this is not actually the way to do this. All right? It's, again, we have to go back to this null hypothesis treatment approach, right? We say, if these two were equal, what would be the likelihood of measuring these differences? All right? And to do this, there's a generalization of the student's t-test for more than one thing. And it's called, there's actually a whole family of these tests. It's analysis of variance. All right? So you can, again, invoke it with R in the beautiful R syntax, as you see there. And you get the same sort of results. You can say if the p-value is below 5%, then we reject the null hypothesis. OK? So we're going to go ahead and say you know, that these things are, in fact, different. So when we compare O3 and O2, we get a p-value of 26.4%. We wanted it to be below 5. That means that we're only 73.6% confident that these results were not due to random chance. In other words, 1 in 4 experiments will show an effect that doesn't exist. OK? So this is a classic failing of the null hypothesis. That is, you can't reject the null hypothesis that -03 and -02 are the same, that all the effects you observe are due to randomness. OK? And you know, colloquially, we say the effect of O3 versus O2 is indistinguishable from noise. Yes?
I agree with the approach of analysis of variance and looking at the null hypothesis, but I didn't see you addressing the case where you have a cutoff point that actually tells you what the sensitivity or the specificity of one test against the other one is. Because
are you talking about the effect size? Is that the question?
Where is the turning point? It's called a cutoff point. When you have two graphs like that, where the mean is a cutoff point. That cutoff point is very important. It tells you by moving left or right. It tells you if your test is really sensitive enough to use this null hypothesis. I didn't see you addressing it because I agree. You cannot say. But the null hypothesis by itself too, because the p, you are choosing the p.
Of course, that's right.
The problem.
But I mean, so the choice of a p-value is always, I mean, this is just the way it works, right? You pick some p-value. Theoretically, the way this whole thing is supposed to proceed is you pick a sample size in advance, you pick a p-value in advance, and then you go and you do your test, right? In fact, this like presentation of the p-value here of 26.4%, you don't use that value. All you do is you say we can't reject the null hypothesis. Right? So that is the sort of standard statistical methodology that I'm employing. Yeah, great. So you know much more about this than I do, right? You've probably forgotten more about it than I've ever learned. I'm more than happy to talk to you about this after the talk. OK? All right. Terrific. OK, so there is this concern about, this is not really a probe effect, but it's an effect of using a tool. Is there something about stabilizer that's hiding the effect? Right? So is there some systematic bias in stabilizer that's changing the effect that we're observing? And so it turns out that we observe all of these speed ups when we run it with -03, -02, -01, or -0. And stabilizer actually, independently of the randomization it employs, adds the same sort of impact to all of them. So it has a fixed additive increase in the number of cycles, the number of branches taken, it's the length of the paths, et cetera, et cetera. All right? It clearly disrupts the memory layout, but that's the point. But every other point in this space where we're counting cycles or we're counting reads and writes and so on, it stays constant. So we end up getting basically the same sort of additive increase.
I'm not sure how you can claim it's the same additive increase, right? So if one optimization, say, is inlining, and one of your big points is about jumping to the stack frame for that method, you're not doing inside of a method.
So is the question right? So do we actually prevent certain optimizations from happening? So we don't, because this actually happens after all the optimizations. So it's an excellent question. So all of this stuff that happens to the code is post-optimizations.
So it doesn't change the inlining decision.
Right, all the inlining decisions, all of the optimization decisions have happened first, and then it goes and it does this.
And there's fewer there's fewer, if they've inlined the methods, then they're not jumping to the methods, so they're not experiencing the randomization of your...
That part is true.
So then I'm just not sure about that these are constant across the different...
So the issue really is, if we take the code that's been produced by LLVM, is stabilizer doing something to it that's disrupting the optimizations? And the answer is no, because all of the optimizations happen first. And then it goes and it does all this stuff to instrument it with randomization.
But the point is valid for inlining.
Yeah.
But by performing inlining, you've now reduced the potential insertion points for stabilizer.
That part is true.
So there's less disruption.
That's right.
In these other.
That's right.
If you
that's right.
00 with 03. Right?
Agreed. One of the good things is that if you go and you actually observe the runtimes of all of these executions, I don't have these graphs here, but they're in the paper. For all but 2 of the cases, if I recall correctly, we get normal distributions of execution time. So you can still do all of your hypothesis testing. The reason that you might not get it is directly related to this problem. It's not actually so much because of code. So how could you fail to get a normal distribution? Well, if you're not actually getting any independent randomizations, then you'll get none. So how can that happen? One giant main. That means no randomization of any functions. There's custom memory allocators. That's actually the big problem. Okay, so some of the spec benchmarks have custom memory allocators. Actually, many of them have custom memory allocators. And if all you do is spend all of your time in one giant array allocated on the heap, then you actually can't randomize within it. That's the biggest problem. Luckily, in almost all the circumstances, it doesn't matter. There's enough other allocation, enough other functions to obscure this. Yeah?
But code layout optimizations like hot code placement are going to be totally disrupted by your...
That's right. I mean, this goes back to Catherine's point, right? So in that case, what you do is you run this without -r code. So you say -r data, -r stack.
Do you see any effect from that?
So
02 versus 03, because I mean...
No, they don't actually do this. So, yeah.
Microsoft compilers...
I know Microsoft does.
Okay. So...
Yes, but LVM does not. All right? So this is just performance of stabilizer. In some cases, it slows things down considerably. Like I said, it slows it down sort of uniformly, but it does slow things down. Thank you, Catherine and Ben. Perl is a disaster. The benchmark is ridiculous in many ways, but Perl is a disaster because it has, it's a giant switch statement with function calls. That's all it does. All right? And so if the functions are placed randomly, then they don't all fit in the TLB. That's really what we see, is we see TLB pressure here. So if we had a hierarchical TLB, we had a bigger TLB, these problems would go away. But that's the bulk of where that cost comes from. And most of them are low. The average is about 10%.
So if you wouldn't randomize, they would fit?
Yeah, so what happens is that all the functions are getting laid out, right? They're just function. So they're very compact. Right?
So they did this on purpose already.
Well, no, it's just an accident of the way that the code gets laid out, right? Nobody randomizes code, right? So the code is just there.
It might not be an accident that it fits in the TLB.
People are smart.
Oh, okay. So I highly recommend you take a close look at the Perl code. there's not that much intelligence happening. Let's put it that
Every
way.
interpreter is structured the same, right?
Yeah, it's a classic interpreter design.
Right.
That's right.
Anytime you take something that fits in a fixed size structure and do anything to it, you now don't fit in the fixed size structure, and TLBs haven't grown in years.
That's right. Yeah.
What about cactus? Why? I totally expected Perl
Yeah.
and GCC to be over there.
Right. So what's happening here? If I recall correctly, this one right here is actually the same problem with the TLB. The TLB is what kills you, but this is for the heap.
Okay.
All right. So we're randomizing
Makes
heap
sense.
locations.
All right.
I thought there was an overhead with Perl just for random diehard.
Yeah, it was
there was a bunch of overhead anyway. So.
But again, it's TLB, right? So
yeah.
So all of this overhead is basically attributable to TLB. There's a second order effect, which is like L3 misses, but TLB kills you.
So you need super pages.
We need super pages. We thought about that actually, but we decided not to actually go that route mostly because Linux makes it a real pain in the neck. It's not like you say, I want to do super. So you have to do sort of, if you boot into your system and you boot into super pages, everything is fine. If you want to actually allocate chunks of memory in super pages, it's a mess. It's really very bad. Yeah.
So it looks like what you need to do, another alternate design point would be to actually still have compact code, but randomize functions within that.
Yes.
Right?
So that's an interesting observation. So part of the problem here is that what we need to randomize. So we undoubtedly have too much randomization. Okay? And we can randomize in a compact way. It is possible. I know how to do it. We didn't do it. One of the reasons is what we actually need to randomize is a certain range of addresses that are the bits that are used in these hash functions, right? And those are actually not the low order bits, right? So they leave off the low order bits, they leave off the very high order bits, and they grab some in the middle. So it's very important that you randomize those. And that is going to lead to things being on different pages. Okay?
That's for the TLB you're talking about.
Yes. Yeah.
So, what does it mean if you slow down 40%?
Yeah.
And I'm going to measure O2, right?
Yep.
This is,
Yep.
I think, what people have been saying.
That's right.
Like,
Yeah.
if I take the original one, that's really the one I'm interested in. And this is like, it's such a huge effect. So.
It has a huge effect. So what it allows you to, so it's important to understand that the effect of stabilizer that is the dilation effect, does not actually affect its ability to discern very, very small differences. All right? It's just a question of running it more times. Okay? So if you imagine, like, all I'm doing is looking for signal to separate from the noise. So if there's a very, very small amount of signal, I will be able to discern it. I just need to run more tests. So having the test itself be slower doesn't actually alter the ability for us to do statistically sound performance evaluation. Now, the result that you get, I mean, obviously, when you run stabilizer, you probably don't want to ship with this, right? But that's a whole separate question. The question is, we're trying to understand whether these effects that we see in performance differences are affected or not. And if both of them get massively dilated, that's OK. Even if those effects are very small, if they're consistent, then we'll detect it.
Right. So your audience is the person who's choosing O2, O3, and making the choice, should I spend the time, to do O3 versus O2? Is it worth it? Right? It's not in some sense the end person who's running the program.
So it's certainly not the end person, but I would say that the audience is actually much broader than the people who are running O2, O3. So my audiences are the following. One, developers who ran their code, and their code seems to run a little slower. They think, oh my God, I got a 2% performance regression. Right? Well, before you go chasing that down, right, find out if that 2% matters, or it's going to go away tomorrow when you modify some more code.
So performance debugging.
So performance debugging.
Performance regression.
And it certainly, well, both ways are meaningful. Certainly if you're like, I have this crazy, super complicated way of doing something, and if I plug this into Internet Explorer, it'll make it run 0.5% faster. But it's going to be a source of bugs and maintenance nightmare and all this sort of thing. Do I really want to do this or not? Right? Is that meaningful? You can decide whether 0.5% is meaningful or not as an effect size, but you need to know if it's statistically significant or not. Right? Then the other audience is really researchers. Right? So researchers publish lots of papers on performance optimizations of all stripes, not just compiler things. Right? Runtime system stuff, different algorithms, lots of things. And there's a kind of, well, seems to work, or the number is large, and you might say, oh, if it's over 20%, that's clearly good enough. But actually, we see larger than 20% swings just by doing static, like link time, like change the link order, change the environment variables, right? You can easily get a 30% swing in performance just with that, right? So it's important that people, when they go ahead and produce these results, that they know that they're real. But is it for grandma? No, it's not really for grandma, right? Grandma doesn't, or grandpa. I definitely am happy to include both grandma and grandpa in this. It's definitely ageism, but certainly my mother and my father have no idea what's going on. So anyway.
So when the effect is so large.
Which effect? Of your optimization.
No.
No.
When the effect of adding this tool to your runtime is so large, how do you control for its variation? Like of course, more runs, right? But
so its only source of variance is its effect on memory layout, right? It doesn't actually do anything different itself.
It's the observer effect, right? Has two parts to it, right? One is because it's code and it's in the runtime with your program.
Right.
This is something that wouldn't have been in the runtime. So there's some effect.
That part is true.
There's the null effect where it gives you the same layout and it has some performance impact, right? Have you tested that?
So if it
Run
gives you-
stabilizer
right,
and make it generate exactly what it did before, and then what's the overhead there?
Yeah, so the overhead is, again, the overhead is totally swamped by these memory layout effects, right? There's almost,
Interesting. How much overhead
yeah,
is
so
that?
we have measured that. I think that it's on the order of 2%. So this is exclusively from indirection. And actually, Charlie has a faster way of doing this that should make it go away. But taking the traps, so every time you take a trap, then you take some hit. It's tied to the frequency with which you do this this relocation. The longer your time delay is, the less you see. There is a small effect on straight line execution of code without randomization. It's very, very small.
I suggest we let Emery kind of.
Okay, I'll wrap it up. Well, I got to the punchline a long time ago. Yeah, ta-da! The punchline is, I know you've been waiting. And then the cat says to the dog, okay. So anyway, so memory layout, as I hope you all will agree, affects performance, makes it difficult to do performance evaluation. Stabilizer controls for the effective layout, right? It randomizes it. This lets you do sound performance evaluation. And we did a case study. The case study shows that, in fact, -03 does not have a statistically significant impact across our benchmarks. And you can actually download this today. It's at stabilizertool.org. And I want to thank the NSF. And sorry, guys, I want to thank Google for helping to fund this. And Google also is funding Charlie's PhD. So he got a PhD fellowship from Google. So anyway, that's it. Thanks for your attention. And I'll put up one backup slide here. So this is -02 versus -03. Yeah.
Did you verify that stabilizer results are the same if you change the environment variables?
You mean the performance?
You run it. Your student runs it under his name and under your name, and you get exactly the same results.
So yeah, so it does. It does, because the start and the position of everything really is totally disrupted by all the randomization.
And you verify that.
We verified it. I'm pretty damn sure we verified it. I should say, one of the things, this is the little secret about Stabilizer. Stabilizer gives you performance predictability. Right now, the cost is too high, but it gives you this performance predictability. And you can argue, look, the chances of me being more than 3 standard deviations away from the mean are less than 0.1%, right? And so the fact that you get this actually gives you very, very predictable performance. So it would be completely shocking if you observed anything different. But it turns out that it's immune. So pretty sure the paper actually has an experiment to this effect. Yeah.
Well, I mean, one thing that's interesting is, and it goes to this question, which is, now there are changes in the environment, and some will affect the performance, and some won't. So the claim is that the environment variable shouldn't affect the performance.
Right.
If I change the library, maybe it will, maybe it won't. Might make something faster, right? But you can actually evaluate that. If I go to a different piece of hardware, you can look at, now with stabilizer, you can say, how do these compare, with stabilizer, compared to without stabilizer. So it seems like, you have a better way to understand the real effect of the environment, which I'd be curious to see in terms of, like, Catherine's done this great work on looking at like 20 different architecture things with respect to energy and things like that. You can do the same thing with stabilizer to see how much difference these architecture changes make.
That's an interesting point. Yeah, I mean, I would be leery of doing this. Well, it's an interesting question. I'm not sure whether the energy impact of the memory layouts, I would have to imagine that would be substantial. But you could certainly detect whether there's a difference. I would have to think very carefully, though, about what the meaning would be of running your stabilizer results on machine 1 and running it on machine 2, right? And comparing them, right? You need to really have a pretty clear null hypothesis. So I guess the null hypothesis would be that these machines have no impact.
Well, I mean,
that would be a very surprising null hypothesis.
For P3 and P4, I mean, I think the Pentium 4, it wasn't clear that it was really better, right? In fact,
yeah, sure.
Yeah, so I'm sure there are cases where you could actually, confirm it.
Right.
Oh, the trace instruction cap. Sorry.
Yeah.
Go ahead, Tom.
Yeah, Tom.
The other question I had was, you could adapt your sampling time or where you relay out.
Yes.
And did you to reduce your overhead, and if you still got acceptable sort of experimental results. So have you looked at that?
So, I mean, we deliberately chose this number because we want to make sure that we would guarantee that we got 30 samples for any reasonable execution.
Nice.
And so you do need to have some number of samples to make using these hypothesis tests meaningful. We are looking at altering the rate at which we do these things based on performance counters for this other tool that Charlie is working on. Yes.
So you're randomizing layout related stuff here, and I can see because of hashing that's a large, but are there other possible effects other than layout that could affect performance? Even with small changes in your code, non-layout related stuff.
Oh, non-layout related.
Yeah.
So I believe that there are. But it's tricky. So I've spoken to one of my colleagues, Daniel Jimenez, who's an expert on branch predictors, and he says that in fact there are other things that you might want to do beyond just laying things out that would actually alter the way that the code behaves in the branch predictor. I'm sure there are many more very subtle things, but he also thinks that those things are second order, that the caching and the addresses themselves are going to be where the big hit is. The question, however, of randomizing things within objects, so you have a function, right, or you have, especially for a function and the code, right, the relative position of them, because they all move together, means that there's a lot less randomization happening. So getting deeper inside would be a way at getting at more possible layouts. Yes.
On this topic, you mentioned offhand the idea of maybe randomizing stuff within a simulator, which seems like it could be really attractive. Like if you have a optimization you want to do to your code and you think this is probably going to speed things up because of instruction scheduling, maybe you'd like to factor out the cache geometry by randomizing that.
Right.
Make sure that your optimization is getting the speed up from the source that you thought it was.
Sure. So there's actually some work. I think it's Mark Hill, if I recall correctly. It's either Mark Hill or David Wood, somebody in Wisconsin, where they actually do inject some randomization into simulation to try to get some error bars, because otherwise everything's exactly the same all the time. But they haven't done, to my knowledge, nobody has done anything like this within a simulator. It begs the other question, obviously, about simulators.
Not on purpose.
Yeah, right. Not on purpose. That's right. It begs the question of simulator fidelity to the real platform, but that's always a question. So, yes.
My question kind of piggyback on what some of us have said. Okay, you are randomizing the layout here. Did you consider other factors, and how did you determine that the highest variability that you might have come from layout?
So I can't say that we've considered every factor, right? What we did is we said, we.
Can you give me a set of factors that you have considered, and how you came to choose layout?
Oh, beyond layout. So it turns out that, so we focused on layout, actually, specifically because it has two very direct consequences on very, very performance critical pieces of your hardware. One is the cache, and one is the branch predictor, right? So the cache is huge, right? If you miss in the cache, you go all the way out to RAM. It's 100 times slower than if it were in L0, right? So this is a gigantic, gigantic impact. Branch prediction has a much less dramatic impact, but it also has an impact on performance, right? So that's why we focused on layout.
Okay, so within a function, the branch layout matters a lot. Like that's an optimization that has a lot of impact on performance.
Right.
So how would you generalize what you did? You'd have to change the compiler because the offsets are baked into the code because you don't want to look up the offset of the else branch, right?
Yep, you're absolutely right. So Charlie and I have talked about this. I guess we should wrap this up very quickly. Briefly, the idea is that you generate different variants of the code. You generate different functions, and then you sample those at execution time. So when you're doing re-randomization, you don't just take this function and move it somewhere else. You take function version K, right?
K
and so
is good.
K is fantastic. K is always fantastic.
Thank you.
So let's thank everybody.